And welcome back. As we continue our exploration of the sun, we previously looked at some early theories of how the sun was producing its energy. So today, let's go ahead and look at a more modern interpretation of how mass, energy, and the theory of relativity all play into how the sun actually produces its energy. So the first thing you have to understand is when we're talking about energy with the sun, we're talking about converting matter itself into energy. The remarkable equivalence between matter and energy is given by one of the most famous equations that we know, E equals mc squared. E, of course, stands for energy, m for mass, and c is the constant that relates the two, is, of course, the speed of light. Now, notice that this formula does not tell us how to convert mass and energy. It's simply just a formula to do so. Scientists very soon realized that the conversion of mass and energy is the source of the sun's heat and light. We can calculate the amount of energy radiated by the sun could be produced by a complete conversion of about 4 million tons of matter into energy inside of the sun each second. Now, destroying 4 million tons of energy seems like a lot when we compare it to things here on Earth, but again, bear in mind that the sun is actually a giant reservoir of matter. In fact, we will see that the sun contains more than enough mass to destroy such amounts of matter and still continue shining at its present rate for billions of years. So the very first thing we need to understand when we start talking about converting mass into energy is this idea of elementary particles. The fundamental components of atoms are, of course, the proton, the neutron, and the electron. Now, these, of course, are very fundamental elements, but these are by no means all the particles that exist. First off, for each type of particle we have, there's a corresponding opposite antiparticle. If the particle contains a charge, then the antiparticle has the opposite charge. The anti-electron is, of course, the positron, which has the same mass as the electron, but is positively charged. Similarly, we have the antiproton, which has a negative charge. The remarkable thing about such antimatter is that when a particle collides with that of its antiparticle, the original particles are annihilated and substantial amounts of energy in the form of photons are produced. And so that's going to get us into this conversation about something that super nerds might understand of neutrinos. In 1933, physicist Wolfgang Pauli suggested that there might be another type of elementary particles. So we already have been theorizing, of course, about like electrons and positrons and protons and whatnot, but what else could there be? Because energy seemed to disappear when certain types of nuclear reactions took place, which we know violates the law of conservation of energy. You can't simply just have, energy, things can't be created and destroyed, with mass. So what's going on here? Well, Pauli was reluctant to accept the idea that one of the basic laws of physics was wrong. And he suggested a so far undetected particle, which is given the name neutrino, carried away this missing energy. He's like, well, it's not that what we're seeing is wrong for the conservation of energy, it's rather that we just haven't detected it. And he suggested furthermore that neutrinos were particles with zero mass, and that much like photons, they moved with the speed of light. Now, neutrinos, of course, were eventually discovered and proven to exist, and however, they don't have zero mass. All right? They were found to have a mass, but it's very, very small, even smaller than that of an electron. And so let's go ahead and keep all this in mind as we look at our atomic nucleus. The nucleus of an atom is not just a loose collection of elementary particles, protons, neutrons, electrons, but are actually held together by a very powerful force, which we refer to as the strong nuclear force. This is a very short-range force, and is only capable of acting over distances about the size of an atomic nucleus. You go past that range, the strong nuclear force cannot work. Now, the strong nuclear force is what we refer to as an attractive force. It wants to bring things together. This is much stronger than the electrical force, and it keeps the particles of the nucleus tightly bound together. So, when we look at the different protons and neutrons that are bound within the nucleus, it is this strong nuclear force that's acting as effectively the glue that holds them together. Now, if particles come together under the strong nuclear force and unite to form an atomic nucleus, well, some of the nuclear energy within is released. The energy given up in such a process is what we refer to as the binding energy of the nucleus. So in order for those protons and stuff to bind together, there's a little bit of energy that is released. When such binding energy is released, the resulting nucleus has slightly less mass than the sum of the masses of the particles that came together to form it. So measurements show that the binding energy is the greatest for atoms with a mass that is either near that of the iron nucleus, and it's going to be much less for both lighter and heavier nuclei. So right around iron is the sweet spot for seeing the most amount of binding energy. Iron, therefore, has to be one of the most stable elements. Since it gives up the most energy when it forms, it would therefore require the most energy to break it back down into its component particles. What this means is that in general, when light atomic nuclei come together to form a heavier one, all the way up to iron, mass is lost and energy is therefore released. Now, this joining together of atomic nuclei is what we refer to as nuclear fusion. Now, energy can also be produced by breaking up heavier atomic nuclei into lighter ones in a process called nuclear fission. Now, nuclear fission is a process that many of us might be familiar with because this is the process that we as humans learn first, in atomic bombs and in nuclear reactors, which are used to generate electrical power. Now, fission also sometimes occurs spontaneously in some unstable nuclei through the process of natural radioactivity. In fact, it's how some of the nuclear decay is worked, is that these things fissure apart. But in order for fission to really occur within the natural environment, it requires big, complex nuclei, such as uranium or plutonium. These are big, heavy nuclei with a ton of things in them. Whereas if we look at stars, we don't see these big, heavy nuclei. Instead, we see predominantly small, simple nuclei, such as hydrogen and helium. So what we have to do is actually look to fusion to really explain the energy of the sun and the stars. So let's look at this through nuclear attraction versus electrical repulsion. And every nucleus beyond that of a simple hydrogen has 2 or more protons. And all protons have positive charges. Since like charges repel via the electrical force, the closer we get 2 nuclei to each other, the more they want to push away, the more they want to repel. So if you had like 2 heliums and you're like, I'm going to try to smush these together, they're going to fight harder and harder. And it's true that if we can get them to kind of come together within a striking distance of each other, well, they're going to smash together with a much stronger attraction because, again, that strong nuclear force is going to take over. So how can we get nuclei close enough together in order to have them participate in such fusion? Well, the answer for this turns out to be a tremendous amount of heat, which speeds the protons up enough to overcome the electrical forces that try to keep them apart. Now, inside the sun, the most common element that we find is hydrogen, whose nucleus contains only a single proton. Now, 2 protons can fuse in regions where the temperature is greater than about 12 million Kelvin. So once we reach that threshold, we can start seeing some of that fusion happen. Now, nuclear reactions in the sun's interior are going to have kind of a 3-step process that takes those, say, about 4 hydrogen nuclei, and is going to fuse them together to form a single helium. Which, you're like, wait a minute, we've got 4 hydrogen nuclei, and we're only going to produce 1 helium. Does that make sense? Yes, it does, because you remember, a helium has 2 protons, and what's going to happen to those other ones? Well, we're going to talk about those. The helium nucleus, first off, is slightly less massive than the 4 hydrogen nuclei that combine to form it, and that mass is converted to energy. Again, some of these things are going to make sense as we move through here, why we need 4 hydrogen in order to form 1 helium. So this is what we refer to as the proton-proton chain. And if we look at step 1 of the proton-proton chain, what are we going to find? Well, the first step in converting hydrogen into a fusion of helium is that we need high temperatures. And these high temperatures are required because this reaction starts with 2 hydrogen nuclei, which are protons, which we have diagrammed here in blue, that must overcome electrical repulsion to combine, forming a hydrogen nucleus with both a proton and a neutron. Now, you'll note that hydrogen by itself is how we usually typically find it, but when we have a proton and a neutron, we get a special form of hydrogen, deuterium. Now, Also produced in this reaction, you'll notice, we get a positron and a neutrino. And again, this is only step 1. And what we've done, of course, is at this step, we have some matter and antimatter that have been formed. So the second step now of this reaction is to continue kind of what we started. This step is going to combine that one hydrogen nucleus, which is a proton, with the deuterium nucleus from the previous step. So again, here's another hydrogen coming in here. It's going to combine with this hydrogen and neutron, because we have one proton, one neutron, so they're coming together to combine. And the product of this is an isotope of helium, so we do have helium now because we do have 2 protons. And we also have a neutron, and then we have energy that is being released in the form of gamma ray radiation. Now, this is not the end. It's like, oh yeah, we got helium here, right? Well, the thing about this is that this is not necessarily stable, because at this point, we have a neutron that's just hanging out here. And let's see what happens. So step 3 of this chain is to, again, continue that fusion that we had seen before. You'll notice that now we have 2 helium nuclei from this previous step that are going to combine before we get to our next step. In here, what happens is when these 2 heliums combine, you'll see that we now get a much more stable helium with 2 protons and 2 neutrons. And the hydrogens are then released here. You can see that these are now released. And this allows that hydrogen to be released to be reused as fuel, which is, again, probably the reason why the sun just doesn't immediately use up, because some of those hydrogens are released back out to be used in the cycle. And so when we look at these proton-proton chains that we just looked at the temperatures inside of the stars with masses that are smaller, all the way up to about 1.2 times the mass of our sun, which, again, this category includes our sun, most of the energy is produced by a set of reactions called the proton-proton chain, which we just looked at. Now, in the proton-proton chain, protons collide directly with other protons to form helium. Now, in hotter stars, so things that are beyond that 1.2 times the mass of our sun, we get a totally another set of reactions that happen, which is referred to as the carbon-nitrogen-oxygen cycle, or CNO. And ultimately, this kind of accomplishes the same net result. In the CNO cycle, carbon-hydrogen nuclei combine to initiate a series of reactions that form nitrogen, oxygen, and ultimately helium. The nitrogen-oxygen nuclei actually do not survive, but interact to form carbon again. Therefore, the outcome is the same as in the proton-proton chain. You got 4 hydrogen atoms that disappear, and in the place, a single helium is created. The CNO cycle plays only a minor role in the sun, because, again, remember, the sun does have some of these gases, but it's, again, mostly hydrogen. And so the main source of energy for stars with masses greater than or about the sun is going to be the CNO cycle. When you're the smaller to about 1.2 times, again, we're going to rely on the proton-proton